5 after, so I'm going to go ahead and get started. Just like I put in the Discord, if you have any questions, just feel free to speak up or type them in the chat. I do have it on my iPad down here. I figured I'd start with just some concepts. Like every engineering class, your exams technically comprehensive because concepts stack on top of each other, but just so y'all know, it's mostly chapter 7, 8, and 9. You still need to know Ohm's law and Kirchhoff's laws, but that's kind of secondary to the 7, 8, and 9 concepts. So I'm going to start off on the right screen. There we go. So I'm going to start off with just some vocabulary because these are things that are... Engineering's full of really, really specific words all the time. So we've got the normal stuff. We've got voltage. We've got current. And we've got resistance. But I'm gonna use impedance. And that's because impedance is the same thing as resistance. So impedance is literally resistance on the complex plane. They're the same thing, it's just this only has a real component. And for the majority of this class, we only needed the real component because resistors only have that. Impedance is the more general term. So we're gonna use that, or at least I'm gonna try and remember to use that. But honestly, need to just let these two be interchangeable in your head. Impedance implies that you're probably going to be dealing with I, but besides that, same difference. And so we have, let's see, you've also come across the words inductance and capacitance. And then there's the concepts of like power and energy. And none of these are connected very clearly in the textbook. And like the last time you talked about work, power, and energy was probably in physics 1 or 2, and you were probably talking about a ball and it moving, or it being very high up, or it being very high up and then moving, or something like that. And it's very hard to kind of make that jump between a ball and electrons. So that's kind of why we're starting here, because these are the words that we need to talk about electricity, but we never explicitly explained them. So if we start with the concept of the ball, we know that this ball, if it's sitting still, it has no kinetic energy. If it's very high up, it has a bunch of potential energy. But what that energy is its ability to go. It may be going right now, or it may be at rest and waiting to go, but it's the ability to go. Well, in a circuit, voltage is the electrical ability to go. This is why you'll also hear electric potential. or just potential, and it means voltage. So voltage is a form of energy, which is why we can get power out of it by calculating voltage times current. But what exactly is power? Well, power's the rate at which energy transfers. So this is how much energy you either need to put into the ball to make it go, or how much energy the ball can put into something else while it is going. So rate at which, and I've got to erase my little diagram. Rate at which energy is transferred. So in a more specific term for circuits, this is the rate of energy between the voltage source and the charge carriers, which is to say the electrons in this case, or at least, to simplify it. So we can call this the rate of energy, and remember we said that voltage is our energy, to charges, or transferred to charges. And then it can also be from charges to whatever the end result, whatever you want the output to be. And so that leaves us with inductance, capacitance, and current. These don't really have analogs to ball physics, to Newtonian physics. Current is more like a velocity than anything else. This is the rate of currents, or more, the rate of charges. So, the dq dt. It's literally how many charges in how many seconds, which is how you get amps. So this is, let this be more like velocity in your head. And when you let it be velocity specifically, you know that it has a direction. And, well, whatever plus or minus is, the sign of the current is its direction. So that's how this can relate to these. And then inductance and capacitance are kind of literal. So inductance is a term for inductors, which are this curly wire. And we know a few things on DC and AC about how these behave. But basically, what this is this is a battery for magnetic fields. This sloshes current back and forth, and it holds a magnetic current here because basically electricity goes in one direction, and then 90 degrees off of that is magnetism. So they're coupled. They're stuck together. Anytime you have electricity, you have magnets. Anytime you have magnets, you have electricity. So like if you have a motor, just a good old-fashioned motor, and you plug it in, it's going to output work by getting electricity. But if you unplug it and you put a crank on it and you put in work, you're going to get out electricity. That is because electricity and magnetism they're combined. So Inductance is basically how much it can, how much magnetic field energy it can store. And then capacitance is capacity. So electricity is induced by magnetism, but electricity is just stored. So it just has a capacity. Let's see, and I've got a question in the Discord. Okay. Question regarding power and current. Because you're confused about how they differ. Since you can describe current as a velocity of sorts, can you also describe power as an acceleration, or does it work somewhat differently? Actually, yes. Yes, your instinct is correct. So, we know that, well, okay. Power is something, okay. You can have power in objects. So like Newtonian physics is where we get ball physics. Everything is a ball, and it's either shot out of a cannon or it's dropped off of a ledge or whatever. So in Newtonian physics, that's kind of where we start, because it's you can see it. So we have things have intrinsic energy, and that energy might make them go, or it might, be stored up ready to go. But once things are going, we have power. Power is, so the textbook definition is rate at which energy is transferred, but it's basically how fast you can get it to go. Not how fast it's going. So how fast it's going is velocity. But how fast you can make it go, like, but start it going, that's power. So this is why we can talk about horsepower, is literally 15 to a horse. Don't ask me why there's 15 horsepower to a single horse, but there is, or why I know that off the top of my head. But I may have converted horses and light bulbs at one point. Silly math. It's like I may have lost track. There we go. Okay. So things, power is not acceleration, but it comes from it. They're intimately related. So let me see. So I don't recall off the top of my head the equation for power from a not circuits point of view. Pretty sure it's work over time, which makes it which is force and distance. Okay, so power is force times distance over time. So it's still a rate. Energy is not a force, but comes from, it's related, but it's not quite directly related. So power in Newtonian is force times distance, and this is just going to continue doing this, isn't it? There we go. Okay. So Newtonian. So in this case, since we have voltage as energy, and we have current as a Q over T, we have to be able to we don't really have a concept of distance in a circuit. So we need to find what the parallel for distance is going to be in the force. So this might end up a little bit further off what we are, or what you need for this class. And I'd be very, very happy to help find a deeper answer for it. Because there are an awful lot of weird parallels. But they're not super intuitive, and some of them take a good bit of math to get to. So, if that's all right, that I'll help you find that answer in a different setting, then I will move on, and then we can circle back to it. Okay, so, and then capacitance is, of course, the kind of easier one to understand, of how much electric energy you can store. So we'll start with these, and I apologize if I've completely buried the lead. But I promise that having these ideas fresh in your head will help. So next thing we're going to do is we're going to look at kind of the tools you need. This is your bag of tricks. This is your toolbox. Things like Ohm's law. Ohm's law is V equals IR, which means that if you have or can find 2 out of 3, voltage, current, resistance, then you have the third one. So then, of course, there is Kirchhoff's laws, Kirchhoff's current law, which is used for node voltage analysis. And that's the one that says that the sum of currents through a node equals 0. And then you've got KVL, which is used for current mesh analysis. It says analysis, I swear. And this is the one that says the sum of voltages in a closed loop equals 0. So the reason, just keep reminding yourself that the reason that node voltage uses the current law is because you are finding voltage in terms of current. No, there's no E at the end of find. And then the same, or the inverse for current mesh analysis and voltage law, is that you are finding current in terms of voltage. So, also you need to know some trig, and that is always a bummer. So, just the stuff that we need to talk about eventually. Phasors. Yay, phasors. Nobody likes phasors. So, see? Can you scroll up a bit? Yes, I can. Here we go. Is that good? And I will also post the links to this and this video eventually, you know, once we're done here. Alrighty. Is it good to keep going? Alright, cool. So, my pleasure. So, triangle stuff. This is a really busy, ugly triangle. So normally we use capital letters for angles and lowercase letters for lines, and you label them with the lowercase letter opposite the angle that is the capital letter. That's why this is set up this way. Theta and phi or phi, whichever one it is, these are just generic angles. This one's the 90-degree angle. None of this all requires right triangles, but that's okay because you don't have to think about that. It's all somehow right triangles, because math is weird. So general stuff. Cosine theta is adjacent. So this is theta. This is the adjacent line over hypotenuse. That guy, the one that's opposite the 90-degree angle. So cosine is b over a. No, I labeled these wrong. This one's supposed to be c, this one's supposed to be a. There we go. B over c, yeah. Sine is opposite, so this one, opposite theta, over hypotenuse, that guy. So a over c, and then tangent, which I wrote out for some reason instead of using the abbreviation, of theta is actually sine theta over cosine theta, which makes it come out, so trig shit. Always comes down to weird trig shit. Oh. The hypotenuses cancel because they're opposite, so, or because they're inverted. And so we end up with over the adjacent over the opposite. So if this is theta, this is the adjacent, this is the opposite. I wrote this backwards. Yeah. Sine is opposite over hypotenuse. And cosine is adjacent over hypotenuse. Still cancels. End up with opposite over ADJ, which is this guy, A, over this guy, B. And this matters because we want to take, because if you need to get an angle, if you need theta, use tangent. So specifically you need to take the arctangent of tangent theta equals theta. This is a button on your calculator. You don't have to figure out what it is. I couldn't tell you if I wanted to. This is a button on your calculator. It might also say that. These are the same. These are the same thing. It just depends on your calculator breed. But either way, if you need theta, this is what you do. So last things are, how do you get the length of something? Or magnitude is square root of x squared plus y squared, where you have some basically you've got this and you were given a something in complex terms, so x plus jy. One of these was supposed to be a j or a y, I mean. So it's these. How you get this length is x squared plus y squared. Leave the j out. Let's see here. Yeah, so those are the major things, just the tools you need to have on hand. Also, for the sake of dealing with me, this is magnitude, because this is the vector m. A vector has a magnitude and a direction. This is the magnitude. So, all right. Now we can get on to the concepts. All of this was just necessary toolbox, which is kind of obnoxious. So chapter 7, 8, and 9 kind of play in together. And I'm going to start with chapter 9. I'm going to be kind of loose with what chapter I'm working on, because they do kind of blend into each other. But we're going to start with chapter 9. We're going to start with chapter 9 because it's talking about sinusoidal signal. So, and I know that's not what the chapter is called, but that's what it's talking about. So, what that means is we got these. We got wiggly boys. And there is some value up here, some magnitude. I'll just use it m because it's pretty generic. But what that is it's going to be a voltage or a current or power, whatever. All of these things can oscillate. And oscillate just means it goes up and down like this. So we've got these. These are sine waves. Actually, this specifically is a sine wave. It starts at 0. It makes a full cycle at 2 pi. Let's see here. Don't do that. But more importantly, it starts down here. For some reason, we don't like to do that. For some reason, we prefer cosine, which starts up here. They are shifted 90 degrees from each other, and we'll get back to that later too. But just for now, these are waves. They exist. We don't necessarily like them because they're frustrating, but they're necessary, and we can do some cool shit with it. So, waves have a frequency. That frequency is basically, so it is 1 over t. T is the period. And period is how long it takes to finish one cycle. So what t this is. If this is t aught, this is t in, right? So 1 over t in is our frequency. This is in cycles per second or hertz, because trig is painful. Not kidding that's how I remembered that unit. Um, so we've got this. Waves have frequency. We choose to talk about frequency as 1 over time, or more 1 over period, instead of talking about time, because we can get more stuff on the graph that way. Because we can very, very definitely write this with t on the x-axis and whatever our interesting value is on the y-axis. But that's all we get, and time is always happening, so it's not really the characteristic thing that makes this wave change. Yes, it changes with time, but what else affects it? And what else can we use? So we actually start to talk about angles instead. So we rule the so we created this omega, which is the angular frequency. And what it is 2 pi times the frequency. So why? 2 pi is a circle, but also it's one cycle of sine or cosine. So this to this, 2 pi. Either one. They are this is why they're interchangeable, and because they're interchangeable, we picked one. Now we picked cosine, and I don't know why, but we picked it. It's what we do. So we have a standard, and so we can write this wiggle as in a standard equation. So it's going to be whatever our interesting value is, whatever's on y, as a function of time is the magnitude of it, or its peak, or whatever, cosine omega t plus theta. And this is something worth writing down, because you're going to have to convert all of your answers into this. Present answers in time domain. When appropriate. I mean, sometimes you're just going to be asked for impedance, and I don't think that that's required to write in this form, but so when dealing with voltage, current, or power. Voltage, current, power. Okay. So we've got this. And if you need to convert, you can convert. Convert sine theta to cosine by subtracting 90 degrees. So it becomes, so sine theta equals cosine theta minus 90. So minus sine theta is cosine theta plus 90. And it's like that. So also something that you might want to have written down. So how does this get us to signal? And by signal, I mean voltage, current, power, that kind of stuff. So we have seen just numbers for voltage so far. Or, before chapter 9. Before chapter 9, voltage was nice because it was only one number. It wasn't a function. Well, so if you have voltage as a function of time, but you choose time, what do you have? you've got just a number. So I choose to think about DC voltage as just a moment in time. It's whatever voltage of T is here. DC is like a snapshot of AC. So this at least helped me figure out how to think about the two of them, so that one of them's not this super alien different thing all of a sudden, but it's the same thing, because honestly, in the real world, you're gonna get fluctuations. It's gonna change with time. So this is just it at a moment. So we're good. So the difference is that usually we've been given voltage as a positive number. So we need to understand kind of what happens when voltage is not a negative or is not a positive number. What happens down here? So I'm going to draw out a circuit that you may or may not have ever seen before, and it's probably going to be freaky because you don't know what the circuit element is, but I will explain it in a moment. So these are diodes. You know what this is? This is a resistor. This is the best way I can explain it, but this is a 320 concept. But I think it's something that you should see. There we go. So this is a circuit. These are diodes. Diodes only let current through in one direction. So current goes through this way. If your current is going this way, you have an open circuit. So it cannot pass. So this is a rectifier circuit. And again, this is a 320 concept, so don't freak. You're not tested on this. This is just an example. But it's kind of a cool one. So we've got this voltage source, and sometimes it's positive, sometimes it's negative. Well, so what happens when it's positive? If you've got V positive, it's gonna come up in one direction, and it's gonna hit this node, and this is an open circuit, so it's going down this way, and then it'll cross back here, and it goes this way. But only on the positive side. When you hit this point, and it starts going down, well, we've got V negative, and it's going to come down, and it's going to come to this point, and it's going to say, oh, well, this is open, so we're going to go this way and cross, and now you have constant power, constant voltage crossing this resistor, and this resistor is just a device. This is your laptop battery. This is an LED. This is whatever needs to have constant power instead of, whoops, well, it hit 0 and it's crossing to the negative side, and we can't use it until it's back up to positive again. This is what's happening in a AC, in an alternating source, is it's powering half the circuit half the time, or it's powering it in one direction half the time. Because half the wave is positive and half the wave is negative. And this is especially important for inductors, because inductors don't make any sense in DC. So inductors are these guys, right? So in DC, it just goes straight through. Now it goes a long way because there's like, meters of, that's probably an exaggeration, but like there's a ridiculous amount of wire here, but it's just going one direction. So the electrons are going in one direction, and the perpendicular magnetic force is just going in one direction. And that is something that I should explain. So you've got a piece of wire or something, or just an electron. And it's got a movement vector of this way. So it's acting in this direction. It has a magnetic force that is perpendicular to that. So this is its magnetic force, and this is its basically electric force. They're going like this. And as long as it keeps going in the same direction, this little guy's fine. This little guy's happy. Nothing weird happens at all. But if you're on AC, you're not going in the same direction all the time, because half the wave we're going this way and half the wave we're going that way. So this little guy in here, he's here, and sometimes he thinks he's going this way and sometimes he thinks he's going that way. And well, so this follows the right hand rule, which means that when he's going this way, his magnetic force is going that way. But when he's going this way, his magnetic force is going that way. So this guy is just like freaking out, losing his mind. He is stuck. He is stuck here because he's not the only electron, and all of them have a magnetic field that is switching back and forth. And they're switching back and forth in the spiral, and it makes them stuck. And it stores energy there. This is why inductors take time to charge, because you have to get up to that point of being stuck to where it can't move. And so this is why they don't make any sense. This is why we just treat them as as a short circuit. As a short circuit on DC. Because it's just a wire. It's not doing anything else, and it physically can't do anything but be a wire. Except when it's on AC. So, and there's a similar for capacitors. Capacitors are really made or intended for situations like this. But they actually do still work on DC. But it is the charging time, basically, that makes these an open circuit. When you have a DC source on capacitor, basically this thing is just charging. It's filling. It's consuming all of the electrons, and none of them are making it out to the other side. You got current coming in this way, and you don't got it coming out the other side, because it's gonna fill itself up. And anytime you don't have current coming through, it's gonna start draining, which means it's got room to fill up again. So this is kind of the logic behind those behaviors. So back to this stuff. Back to the waves. Back to the really crooked lines. Okay. So back to the waves. We know that time is always happening. So we don't really need to focus on it. Also, we kind of need to see a lot of data, and if this is already dedicated to time, then we can't look at the angle as well as time. So we look at frequency. This is frequency. This is, right, 1 over t. And we know that time is buried in here somewhere. So we're basically letting the angles and time be on the same axis. So you can have now multiple waves on the same thing, and it's understandable. So if this is 90 degrees and whatever all the way down, then we can talk about, so let's say that this is the main M function. This green one is lagging. This is lagging M. And the blue one is leading M. This may or may not come up in life, but it is something important to understand. So we're talking about frequency now. We're talking about angular frequency. That whole 2 pi f. So this again, it just lets us see more stuff. So how do we get this in circuits though? So we deal with this because AC is complicated. AC requires us to admit that the signal might change. We also have so once we are out of time domain, so time domain being the t is on the x-axis. Once we're out of that and we're into a frequency domain or a phase domain, we can start talking about impedances and things like that. And this kind of gets us into the more complex circuits. So, we've got, and this is the chapter 7 and 8 stuff. So, we've got more complex circuits. So, we know that the first order are the RL and RC circuits. These are the ones that have a resistor and an inductor, or a resistor and a capacitor, but never the two shall meet. This is a first order ODE, and differential equations are a big can of worms. So in the textbook, I think it shows some of the derivations, but for the most part, just use the equations that are boxed. That's the result of the differential equations that are produced by RL and RC circuits. So let's see here. So in these, we need to well, let me write out the second order too. So second order equations are RLC circuits, and those are the ones that have all three, like that, or some combination. And these are second order ODEs, or ordinary differential equations. You can derive them. You can't. It's, well, That's kind of a grad student thing to say. It's not that hard, but so you can do it. And if you're interested in doing it, I would be happy to go through it with you. I will not, however, force you to sit through it. Um, so all I will say is that the differential equation comes from the characteristic equations of the circuit elements. So that's not a capacitor. I don't know what that is, but it's not a capacitor. There we go. So we've got these, and this is whatever voltage. We've got a resistor, we've got an inductor, and we've got a capacitor. And we have characteristic impedances for them, and we also have characteristic voltages for them. And you know what that means, or, well, okay, well, we have some characteristic thing about them. We might have a voltage. We might have a current. I'll tell you this. Inductors don't really care about voltage. They care about the current. But all of them have impedance, so we can talk about that. So, and actually we can define all of these with terms of voltage, but so I will give this just to make it easy. So inductor has a impedance of imaginary omega L, j omega L. And it has a voltage of L di with respect to t dt. So this is so when you see lowercase I as a function of t, it means DC, or it means AC. Just expect that this implies AC. However, it doesn't have to be, but generally, if you're gonna do derivatives or integrals, it expects to have a function. So you got that. Resistors just got R, man. It's just like that. Their voltage, real simple. That's Ohm's law. It's Ri. I'm sorry. It's yeah. And then there's capacitors, and capacitors have an impedance, and that impedance is minus J over omega C. And their voltage, generally capacitors are talked about as their current, but you can talk about them as voltage. It's 1 over C integral of I as a function of t dt. Now, if you were to take Kirchhoff's voltage law of this, and you were to say there is some uniting I, that there most certainly is, there's a current around these, you could write that out, and that's how you get the differential equation. That's where it comes from. And I will write it out, and then we will never look at it again. That is my promise to you. So we're starting here. R times I is the voltage. Then we're going to go here to the voltage of this inductor, which we said is plus L d I dt. And then we're going to go to this capacitor, which is 1 over C integral of I dt. And then we're coming into the negative side of this bad boy, so it's minus V equals 0. This is how we got the differential equation. This is why there's differential equations and why we have first and second order differential equations. Now, the reason these become second order is because we cannot handle this with this integral in it. So the first thing you have to do is differentiate this. So you end up with Ri plus L d squared I dt squared. So this is the second derivative of current. That's where the second order comes from. Plus 1 over c I dt minus, and this is a constant. So it's a 0 times 0. And this is where where the book has to start with, and this is why you aren't doing this, because differential equations suck. But this is also why second orders come with very specific weird solutions, like, oh, it's got two real solutions that aren't equal, or it's got imaginary solutions. It comes from the differential equations, and there's no avoiding it, and I'm so sorry. But that is it. That is unfortunately the life. So we have so those are basically the concepts that we needed to talk about. There are the concepts I do want to talk about. Damping. So because damping sure has a lot of words associated with it, but it's kind of weird to try and figure out. So we're going to talk about it with boxes that have mass, and springs. Mass 2, mass 3. Because you want to know something awful? The differential equation you get out of this is the same as the differential equation you get out of this. Or at least, visually, functionally. It's math. So we've got these masses, and they are on springs, and these springs have different spring constants, and you know that's the thing that makes them stiff, or extra wiggly. So the relationship between those is weirdly still, you'd use the same math as up here. So we're not gonna do any math with this thing, but we're gonna talk about what the different forms of damping mean. So damping is what restrains a frequency by dissipating force. So restraining a frequency by dissipating force. That is a scientific definition. What that should tell you is that damping is a resistive force. A resistive force. It is something that gets in the way of the motion. So we have so it's whatever friction is these things are experiencing as they slosh back and forth. It's whatever stiffness of this spring and how they interact with each other, as maybe this one's attached to a wall and these all just pull out and jiggle back and forth at different oscillations because this spring is stiffer than that spring. And so this one doesn't wiggle as much, and this one wiggles way more, and so on. So damping is the thing that inhibits force, frequency, motion, that kind of thing. So we're gonna say motion? But it is motion, right, in a circuit, because you've got electrons skittering around. So the thing that inhibits flow, maybe. Action? So that's what damping practically is. And overdamping is what it sounds like. Overdamp is this spring that we said is really stiff. Well, it's now preventing motion that normally would happen. So, too much Too much restraint. And it inhibits the full cycle from happening. And then you've got critically damp. And by the way, this is the alpha greater than omega odd. 1. So then you've got critically damp. I did something wrong here. Hold on. Critically damp is just enough. Goldilocks. Just enough damping for the full cycle. For the full cycle to occur. And this one is the alpha equals omega odd. And then you've got underdamp. And this one is too little. Too little damping. So the signal goes wild, or the cycle. So these things matter, and this one is the less than. So these things matter in not just electricity, but in motors and machinery too, because when things move, they vibrate, especially if they've got motors in them. They vibrate, and having too much of that vibration, so being underdamped, means that you've got parts rubbing together, or you've got things that have a potential to torque and tear. You've got you will prolong the machine's lifespan if you can get it to that critically damp state. You will have it has to work too hard, and it's inefficient if it's over damp and it's like fighting itself to function. So these aren't just electrical concepts, and you may not get out of differential equations. I hope that you do. But these things have visible examples that we can think of. It's not all just the imaginary electrons and their imaginary values. So the alpha in this case is R over 2L, and these are only for second order. Only for situations where you have RLC circuits. And then the omega odd is square root of LC under 1. That's not how you normally say that. And then the equations you're going to want to focus on are 8.10, but mostly equation 8.14, 8.21. Yes, those are both for second order. So this stuff only counts for second order equations. Anything that has to do with alpha and omega odd. And then these equations that I'm listing, 8.26, are for overdamp, crit damp, and underdamp. So you will need to be able to identify, so basically calculate these of the equation and figure out if it's over critical or underdamp, and then you might need to apply that. Basically, knowing that tells you which one of these three it is. If you were to just do the differential equation, you probably wouldn't have to do this, because, well, I mean, you'd still need to know whether it was one of these, but you would find that out by going the long way and solving this differential equation. You don't need to do that, but you do need to first figure out which one it is, then apply the right equation. That's it. Let's see. And in these equations, you will see a mystery A. A is a generic constant. Um, it it can be 1, say, or 0 if that's not going to change the equation. Um, that is a Muscatel. So that's kind of the content I've gotten. I will probably send you the notes that I wrote this on, as well as this, as soon as I figure out how to get them out of my iPad. Um, so do you guys want to go over some problems? Okay. Do y'all have any in mind? I've got a couple that I thought were useful, but I wanna open the floor to that first. All right, in chapter 7, that sounds good. All right, I have the textbook up, so you just tell me what problem we're looking at. Full disclosure, I also have the solutions up, and we'll be going by those. Okay, that's fine. That's absolutely fine. Was it a homework problem, or was it one that you stumbled on that looked interesting and like it was something you wanted to do? Homework problem? Okay. Let's see if we can find it then. Let's see here. Y'all had 7.3, 4, 7, 10, 11, 12, and 15. Let's see. I think 11 and 12 are probably the, well, 12 was the design a problem, but I think it's a good opportunity. So I'm planning on going over that one. Um, let's see. Let us see what 10 looked like. So do you happen to remember what was included in it? So let's go ahead and look at 7.12. So 7.12 was, 7.12 was the design a problem, help other students better understand source-free RL circuits. So this one told you outright this is a source-free RL circuit. And we were basically given free reign over it. We were given IT happens here, and that this is L, and that this is R2, and that this is R1, and that at t equals 0, this opens up. So we were actually given quite a lot of information about this. So the best, or like the thing that presents itself to me is that current. So if we were to make up a problem, we would probably make it up about that current, especially since we know that t at time 0, this gate opens up. So before t equals 0, so basically minus infinity to 0 seconds. So basically forever before this, we had just this. We had that resistor, we had this resistor, we had this inductor, and everything was happening merrily. We got current this way, and we got currents that split down that way, and of course this inductor has a voltage over it, and this resistor has a voltage, and so does this one, and all of that happened. But since it was basically infinity before 0, we know, or we can assume, that that inductor had plenty of time to charge. The inductor had plenty of time to charge. But now it's t equals 0 and on. So 0 to positive infinity. So from now on, forever from now on, we have this, and it's open. It is an open circuit to this resistor, to this resistor, to this inductor, and they connect here. Well, there is only one complete circuit in this now, and that is right here. This is the only complete circuit. So let's just redraw that. No, not with the highlighter. Let's not draw that with the highlighter. We've got a resistor, and we've got a fully charged inductor. So that means we got current. We got current, and hey, we happen to be given the labeled current. The current is IT. Sweet. So what can we do about that? So we can find that. We can find current. And that's what the problem statement of this theoretical question would be, is find I of t for time greater than 0. So how do we do that? Because, you know, we have to have a solution manual, right? Because if we don't have the answer to it, then when students come asking for it, we're not going to be able to tell them, oh yeah, this is the thing. So let's go ahead and do that. So we've got that very nice little circuit, very simple little circuit. This is a source-free circuit. And that's how we got there, because, you know, we were told this is a source-free RL circuit, but we were given a source. Well, the source is disconnected, so no longer sourceful. It is source-free. So how do we handle that? Well, so first we kind of need to think about what happened before time equals 0. Before that, we had a DC source, because we would have been told with either this symbol or with V of t that this was AC. So this is a DC source running this, and that means that while this source is connected, this is a wire. This is just a wire. It was just doing stuff. This was the only circuit that really existed. So before t of 0, we had this. We had just a resistor, just a voltage source. It went around. It did stuff. And this current is just Ohm's law. It's just Ohm's law. It's just V. It's just V over R. Over R1. And it's still going to be V over R1 when t equals 0 and it cuts off, for the instant that t equals 0. This kind of problem is very, very confusing, because basically you've got lots of things happening at 0. You've got whatever was happening before the change, and then whatever happened after the change. But the problem is, all three of those things appear at 0, so we have to think about it. We have to think about it, unfortunately, from the negative infinity to 0 side, and then from the 0 to positive infinity side, which makes it very, very weird. But since we know that this current coming out of this simplified half of the circuit is just V over R1, well, nothing else is going to change that, because when this half of the circuit becomes just this half of the circuit, it's still here. It's still there. So it's still V over R1 on this side for this example. And then it's going to start changing. Like, immediately when t is greater than 0, it's going to start changing. But for now, it's still there. So we need the time constant to be able to mesh these together. So for a RL circuit, because this is resistor inductor, so RL circuit, for an RL circuit, time constant is L over R. And that R is R2. Because remember, this one is R2 in our inductor. So this becomes L over R2. And that's it. So if we want I of t, we need I of 0, right? Because we need I0 for this form of equation. Because it's I of t equals I0 e to the minus t over tau in amps. So, and one of our rules of a source-free circuit is that I of 0 is I odd. It's I initial. So This becomes this times e to the minus t over L over R2, which is I naught e to the minus t R2 over L. There we go. And that's it. That would be the form of the answer. If we then, if for this one, since it said make up a problem, if we assigned numbers to it, we'd do the numbers thing. But that's it. That's what we do.